So it's a pleasure to have Abhijit with us. So he's visiting here for 3 days. So he'll be here tomorrow and day after as well, right? Or
No, day after.
day after you're leaving. So tomorrow he's around, and he's sitting in Toshik's office. What? 118. 118. So the Abhijit did his PhD from IIT Guwahati, and then he did his first postdoc from PRL, second one from IACS Kolkata, and now he's in IUP Bhubaneswar. So Abhijit is going to talk about implication of dark matter spike around Sagittarius A on the gamma ray searches of Bino dark matter in MSSM. So over to you.
Thank you, Professor Chalkovich, for asking me. It's very important. So let me start. You can see the title of my talk is Implication of Dark Matter Spike around Sagittarius A on the gamma ray searches of Bino dark matter. This all involves a few things. First of all, assuming dark matter is of particle nature. Secondly, I have considered a SME known as Sagittarius A. Thirdly, I emphasize on gamma ray searches or gamma ray detection prospects of dark matter in MSSM. MSSM means minimal supersymmetric standard model. So this is a supersymmetric theory which talks about extension of standard model. I'll come one by one. First, particle dark matter means dark matter. We need to accommodate dark matter in a particle physics form. The particle dark matter, in the particle dark matter nature, we are a broad category of dark matter candidates. They couple to standard model via wing interaction. So it is assumed that early universe, the dark matter was in thermal equilibrium with the standard model particles. So the distribution, number distribution of the dark matter will follow the thermal equilibrium distribution of the dark matter with the same temperature as of standard model. See, along the y-axis, I have plotted co-moving number density of the dark matter. Along x-axis, it is temperature, redefined temperature, which is the ratio of mass by dark matter mass by temperature. So initially, the dark matter was in thermal equilibrium. It follows the equilibrium distribution. Later, it decouples from the thermal bar and freezes out. So at the moment when dark matter number density becomes almost constant, we calculate the Rayleigh abundance of the dark matter. You can see three different curves are there. This is for increasing sigma. So if you increase sigma b, the dark matter decouples from the standard model bar at a later temperature. So when dark matter gets decoupled from the standard model bar, it has to do with the expansion of the universe. When the number density times the interaction cross section of the dark matter crosses the Hubble, then dark matter freezes out. So when at early times number density was so large that the ratio of interaction rate divided by Hubble was greater than 1 and dark matter was in thermal equilibrium. When the crossover happens, that means interaction rate is not sufficient to maintain the equilibrium condition. The dark matter decouples and freezes out. So here sigma b stands for dark matter annihilation rate, nt is the number density, and ht is the Hubble or expansion parameter of the universe. Now, if for a larger sigma b, the decoupling will happen later. This is obvious because larger sigma b means larger strength to compete with the expansion parameter. So it will decouple at a later stage. The
you said that they are weakly coupled.
Yes.
This kind of part. How will you harmonize first?
Although dark matter is weakly coupled, the cross section, the required strength of the coupling is matches with the weak scale, but still it is sufficient to maintain the thermal equilibrium initially. But at later stage, it gets decoupled.
And when you call initially, what is the time scale?
Initially means we measure it as function of temperature. When temperature is like much greater than the dark matter mass. See here, along the x-axis I have plotted the ratio between dark matter mass and the temperature. So early times means x, this quantity x is much larger than 1.
And then compared to electric scale or
Yeah, I'm coming to that. So in the next slide, the relic density of the dark matter, this is an analytical approximated expression for the relic density of dark matter, which tells you that the relic density of dark matter is inversely proportional to the interaction cross section of the dark. So relic density is defined by the ratio between your energy density of the dark matter and critical energy density of the universe, with rho c is this critical energy density and present Hubble parameter is order of 100. So observation tells us this has to be around point, generally measured by Planck, WMAP and other cosmological experiments, which requires this required order of dark matter interaction state around 10 to the power minus 26 centimeter second cube. So this is an appropriate cross section for a massive particle interacting with the weak force, hence called as WIM or weakly interacting massive particle. Now, this is one kind of possibility. There could be other possible nature of particle dark matter, which are known as feebly interacting dark matter and strongly interacting dark matter. So in case of film, it happens that I have shown the dark matter was initially in thermal equilibrium, but it may happen that it doesn't have the sufficient strength to remain in thermal equilibrium at the universe. Then you have to non-thermally produce the dark matter from the thermal bath. In that case, it is known as film. In SIM, like strongly interacting dark matter particles itself are so strongly coupled, like suppose you have a self interaction among the dark matter, then what happens, even after decoupling from the thermal bath, dark matter can have annihilation among them, like 2, 3. So 2 dark matter particles going to 3. So that is known as SIM. So this is kind of brief picture of particle dark matter. Now, what about searches of the possible searches of dark matter? One is direct detection. So dark matter, assuming dark matter is everywhere, the dark matter can scatter off the standard model particles on nuclear, and we can measure the required energy. That is known as direct detection. Second could be, it could produce the dark matter in the colliders. Like you have standard model particles, since standard model particles coupled to dark matter, you could produce it in the laboratory. This needs, of course, sufficient strength between the standard model and dark matter. For wind, it may be possible, but for film, which requires very feeble coupling, it may not be possible. Suppose in electron collider, you have E minus E plus. That could give you dark matter, and one gamma can emit. So the dark matter, the presence of the dark matter can be measured in the form of missing energy as well as a monophoton. So this could be a possible strategy to look for dark matter at your laboratory. Third one is indirect detection. So in the indirect detection, what happens that we have galaxies. So in the galaxies, there will find clump of dark matter. That means dark matter density is quite high. There, dark matter can annihilate. Since the dark matter density is high, so we will have many annihilation products in form of cosmic rays throughout the universe. So these 3 are possible searches for dark matter. Now I will briefly describe the direct detection. So what happens in the direct detection? So here is a nucleon. We have atoms everywhere. So dark matter scatter off nucleon, and we will find the recoil energy of the nucleon. Here the recoil energy has been expressed in form of the scattering probability as well as the number density, velocity, relative velocity of the dark matter, and also number of targets, this ratio CT by MT, number of targets per unit mass of the detector material. So we have a target, nuclei, dark matter scatters off, and you find recoil events of the nuclei. So you need to find the number of recoil events and whether your observation exceeds this number of recoil events. So using this observed recoil events, you can constrain the d sigma t TER parameter or the sigma t dark matter interaction cross section with the nucleus. So we have this kind of curve where you can constrain. Yeah, there could be background events. So we know because here dark matter scatters of nuclear, so there could be other events involving the standard model particles. We know those kind of events. So when you have recoil events, you subtract those the known events and find out what are the excessive. That is the example. Well, now, so using those recoil events, you can really restrict the order of interaction state of the dark matter with the nuclear. There are different experiments depending on their target materials, like this xenon experiment, xenon NT, they use these xenon atoms. Other experiments also use argon atom. So they used to provide the upper bound on the annihilation, on the interaction cross section of the dark matter with the nuclear. So currently, Lux-Zeppelin provides the most stringent limit. Results of xenon NT is also out, and I heard that is the most stringent limit. But here, Lux-Zeppelin gives you the stringent limit on the interaction state of the dark matter with the nuclear. Importantly, say for high mass, the bound is getting relaxed, as well as for low mass, it is happening too. For high mass, what happens? The number density of dark matter gets reduced because number density is proportional to 1 by MTL, 1 by mass of the dark. So you expect less number of recoil events. At lower mass, what happens? You may have kinetic suppression. That means the experimental sensitivity gets weakened with the reduced mass of the dark. Indirect detection. Please recall that what I have said, you have many galaxies. So in galaxies, you have a huge clump of dark matter. That dark matter annihilates to standard model particles. And those are everywhere, which we can track. So there could be neutral particles, dark matter may annihilate, and there could be charged particles, dark matter may annihilate. So for neutral particles, those will be traveling uninterrupted. For charged particles, they could be interrupted by cosmic electromagnetic fields. Among neutral particles, we may have gamma rays. So gamma rays can be product of dark matter annihilation, or dark matter may annihilate to charged particles. Those charged particles can also emit gamma. There are experiments like Fermi, ICT, etc. They used to track these gamma rays coming from dark matter annihilation. Secondly, dark matter may annihilate to neutrinos also. Super Kamiokande ice cube. These experiments measure the flux of neutrinos coming from dark matter annihilation. Now,
How do you know that those neutrinos or those gamma rays are coming from dark?
So you have to take into account all possible backgrounds. So there could be many sources. You receive the number of total events and you subtract the number of backgrounds.
But how do you model the background? Because for let's say identification material for these, you need to know the galaxies and
Yes. So there will be large uncertainties available. I mean, large uncertainties involved.
From the sun, they will only be neutral.
Yes.
So if you see anti-neutrinos from the sun, then of course it is not coming from the sun. So
you can keep more of anti-neutrinos.
No, solar fusion produces only neutrons. You see something coming, you can say that it is coming from anti-neutron, which I stream for example. Then you can say that this is coming from the direction of the sun, but it is not coming from the solar fusion process. So it is some other source of neutrons. Maybe dark matter annihilation. I mean, the dark matter is annihilating in the sun. But how do you know it's anti-nuclear or coming much behind the sun in the first three months, right? But no, these are produced in the sun. Yeah, but how do you annihilating in the sun? No, how do I know that it is coming from sun?
Different specific energy regions.
That can be because you're tracking it. The probability that some galaxy is going to remain behind the sun all through the year or not from other galaxies, just something where flux was happening. You will know, no? Because they will be offsets. I mean, you know that this, how would the supercale they have a direction from the sun, right? Yeah, but because the sun is there, all other stars in our galaxy goes beyond the sun. Yeah, but they're going fast. They're not exactly rotating at the same. They're not behind the sun always, right? So that's how they will have that time. Right? We have to do that. Yeah. So they do the instantaneous position of the sun. Yeah, it is not important. A longish time. So every event that you get, you will mask back where it came from. Yes. Every but for every event, say I have one picture. I don't know whether it came from sun or some star which was just behind the sun. Statistically, you will know, right?
Sorry. One also energy, right? The dark
Yes,
matter
energy,
is
right.
10 G or 100 G, unlikely astrophysics.
Yeah, that's true. It will not come from the sun. Sun
But
will
if it is
be
light dark matter, then you can have confusion from
Yes.
astrophysics.
yeah,
Otherwise,
you get GB or G still.
Right.
anything, all of it.
Also.
If the dark matter is very heavy, then
Depending on the
astrophysical sources are unlikely.
Yes.
Backgrounds will be much lower rate.
It's only the light.
But uncertainties will be there always. But they would please go through this part.
Yeah, that is always a confusion. There was a claim that it is dark matter. But then many people wrote saying that pulsars can actually produce this, the cosmic ray, the AMS anomaly and all of that, the Pamela anomaly, everything. Whenever you find an anomaly, there will be one community who says it is dark matter, then there is astrophysics people who say that no, pulsars can produce it.
Just
And
like
then you will improve your understanding of pulsars and modeling of everything.
yeah, just like nanograph declared that gravitational wave exists, right? So
It exists.
so papers predicting different sources for that. So you can't distinguish which source is the correct. Well,
But if it is true that dark matter is much heavier, then you have an easier one
yes.
because it is thicker.
So similar to the neutral particles that can result from dark matter annihilation, you could have charged particles also. And if it is electron, this experiment measured the look for the electrons, and also you have experiments that look for protons, antiprotons. So the message of this slide is the dark matter annihilation can result into both neutral particles and charged particles, which you can track and find out what is the mass, or or predict or shed some light on the dark matter mass and its nature.
So are there like particles that are produced from the dark matter? Do they affect the cosmic ray spectrum?
For electromagnetic particles, in principle,
Are there any signatures from the cosmic rays where you have kind of very high energy?
yes. So I think it should be, because when you produce charged particles from dark matter annihilation, it could deviate the path of some other particle. So that you can always track the deviation.
Cannot switch off the dark matter charge. So what you see is some total. You never really see.
Yes.
Then there is no way.
Because the cosmic ray particles are extremely.
There a way
That all we does it by hand.
Efficient channel.
Efficiency of channel.
Yeah, efficient. Particles.
No. See, there are observations for neutral particles as well, for charged particles. You may heard about positive proton antiproton excess by AMS, right? And like there is an excess of neutral particles 5 on with energy 511 keV. So my focus in this work on the neutral particles, particularly gamma rays. Now, the whole thing is about to calculate the flux of the particle that result from the dark matter annihilation. For me, it is the gamma ray flux. I will calculate the differential gamma ray flux. See, this flux involves the dark matter annihilation rate sigma v, dark matter mass, as well as DNI, DEI. I am coming to this factor, as well as the density of the dark matter and the solid angle. So here is the telescope. This is the line of sight. This is the galactic origin. So you want to capture the incoming flux in this telescope. So you have to integrate over the solid angle. This red text is known as the J factor and is calculated by integrating dark matter density along the line of sight and the solid angle data. So it looks that this J factor is an astrophysical factor. It doesn't involve any particle physics information. Given your density of the dark matter is independent of the particle interaction. Now, the differential flux is proportional to the velocity average annihilation cross section. What experiments tell us? Experiment tells us about the observed flux. Once you know the dark matter profile, you can put constraints on the dark matter annihilation strength. What we do, the model builders, we calculate the sigma v, the dark matter annihilation strength in the present universe, considering a particular dark matter profile. Calculate the differential flux, which is restricted by the experiments. Yes. From this is the origin, galactic sector origin, and you have your telescope here. So this is the line of sight. Now I'm coming to the factor DND. So this DND refers to the differential spectrum of ith standard model particle produced for a single annihilation. This includes summation over all possible dark matter channels. Means the dark matter can directly annihilate to gamma, the dark matter can annihilate to electrons that further produce gamma. So all possibilities have been included by the use of this summation. This D and D gamma, this factor we usually calculate by the package Pythia, which does the short. This Fi is the final state. Fi is the final state. It could be either gamma, it could be electron, it could be quarks. Right? Dark matter may have many final states. It doesn't only annihilate to photons. It may have annihilation to quarks also, to electrons also with a particular branching ratio. That's why we sum over branching ratio and a single DNI D.
Branching is the particular model.
Yes. When you have a model, we know all the branches.
So what model?
I'm coming to it.
So, will opting particularly consider
that depends completely on your for a possible. Okay, let me talk about a certain model. Suppose you have a real singlet scalar dark matter phi, which couples to Higgs boson only. Then your dark matter that can further give you gamma rays. So see, when you calculate D and DI factor for this particular model, you have to sum over electrons, all quarks, all gauge bosons, if they exist. You don't have any gamma. Yeah, it may not have a gamma in immediate final state, but if you produce electron, that can give you gamma. I'm coming.
Well, also emission of the final cycle. Photon emission of final.
That's what he's saying. That's what he's saying.
I'm coming.
I have one, right? So this rule that you are talking about, the
Yes.
steady, it could in principle be a function of E or E of the dark matter, right? And then the average thing should go inside, right?
If for a profile, if it is a function of B, then you have to, yes,
Inside the
inside. So I'll be talking about a profile
where you
for
can
which, for which dark matter density depends on your dark matter annihilation state to the part. I'll be talking about a dark matter profile. Here, as I said, the J factor doesn't carry any particle physics information. But I'll be talking about a case where the J factor will include the particle physics. Then the scenario will be different. So same thing, if for a profile, as we were saying, that the density depends on the relative velocity, then the form of integration will be different.
So is it like you were using PTR to calculate this DNI DE gamma, right?
We generated it from the micromega, which uses it. Yes. So as I was saying that dark matter can annihilate to gauge bosons, leptons, Higgses, or quarks in principle. That can further give you gamma and neutrino. So here is a simple case for gamma spectra. Along y-axis you have d and dx, that is the differential spectra of the standard model particles produced. The left one is for gamma spectra, right one is for neutrino spectra.
So you don't include three-body gamma emission.
I mean this plot I am showing you for representation purpose. I picked it up from this paper.
The final number to include.
Yes. In my case, there will be three body masses. Right. Alright. So you can see that quarks give you a soft spectra. So the peak is around lower energy for quarks, and the peak is at larger energies for electrons. So the message is, for final state quarks, you have a soft spectra, soft gamma spectra, and for final state with leptons, you have a hard spectra. This is even true for neutrinos also.
Sorry, why is that?
Because when you have quarks in a final state, it hydrolyzes, then find their spot, then find further decay to gamma. So you have, large energy distribution among different particles.
Crazy.
Yes. For leptons, for final states having leptons, these usually give gamma by final state radiation.
So you're not including two photon annihilation channel.
Two photon annihilation channel will give you light. So there are four possible processes which can give you gamma rays. First one is hadronization. Hadronization is possible when dark matter annihilates to quark and antiquarks. They form hadrons, and among them pion release to gamma. So see here, distribution of energy is large. So that's why it usually gives you a soft spectrum.
This will happen in some 200 MBs. The quarks are around 200 MBs.
I didn't get you.
We're talking about hadronization.
Yes.
It will happen only at the QC.
Yes, true.
These are all
But
very low
confined.
energy processes.
Yes.
No, but the pions can be very highly boosted, right?
Depends on the dark matter
You
mass.
found some magnetization, then it will be pions.
But for hydrogenation to happen, have an energy of 200.
No, that's in the rest frame you should have that. But in the lab frame, the final state is very high energy, right? From the annihilation of the dark matter. So then that what hadronizes to produce a very highly boosted pi zero, which will then decay to gammas, which can be very high.
But compared to final state radiation, where electron gives you a final state radiation. This will give you a Hertz spectra, the final state radiation. Besides, there could be inverse Compton scattering too, where high energy electrons produced in the dark matter annihilation scatter off low energy photons, boosting to gamma ray energies. Here you see that high energy electrons can scatter off low energy gamma and give you a boosted gamma rays. Gamma, this prime denotes the boosted one. Finally, you may have line signal where dark matter directly annihilates to either a single photon or double. Then you will find a peak. Then you can correctly or precisely determine the energy of the emitted photon. Then we will show if dark matter annihilates to two photons or a single photon, you will find a sharp peak in your gamma ray spectrum.
So this scattering of CMB, if it is from the center of our galaxy, is that rate relevant at all, or is that very small?
Yes, it is relevant sometimes.
Is it?
Yes.
What do you mean by sometimes?
Sometimes depending on the energy of the emitted electrons. If your dark matter strongly couples to electron, it may happen that the boosted gamma high energy resulting from dark matter annihilation may have high energy.
No, let's say tens of GeV photons from the center of our galaxy coming to us.
Okay.
What is the probability that there is an interaction with CMB photon? It's a question of mean pickup, right?
Yes.
Is it relevant at all from the center of our galaxy to us? I just don't have a feel for the probability. Is
No,
it completely ignorable, or is it a very important?
I got your question.
Both gamma and the electron are in somewhere far away, right?
No, center of our galaxy. Annihilation happens center of our galaxy.
Yes, center of order.
That is.
Yeah, I got your question, but right now, I'll see it later. Well, so finally, I've talked about line signal. Now I'm coming to dark matter density profile. So you need to model your distribution of dark matter in a galaxy. Two of the most common density profile used in literature are these. You may ask why different profiles are there. One can work with NFW, number of Frank-White, and there is also Eisenhower profile, which is a deviation from the NFW profile. So in the NFW profile, you have a factor RS, which is the scale radius. So below RS, when your radius is below RS, you see a Caspi profile. That means you see a large steep of the dark matter density. Now, dark matter density profile in the innermost regions of the halo, in fact, shows deviation from a simple power law like this, and a better fit could be obtained by Einstein. So what I'm saying that NFW profile is not sufficient to explain each and every microstructure of the gas. And that leads to consider other profiles.
So you're talking about n-body simulation.
Yes.
So that is still controversial, right?
Yes.
Whether it is needed or
Yes. But since cold dark matter has many problems like core cast problem, so you may have a core profile or cast.
well, that is still controversial.
Yeah, that is also. So here I have plotted the density of the dark matter as function of R. You see, at R less than 10 to the power minus 3, there is a significant deviation in the density. So this tells you that if you calculate the gamma ray flux, considering either NFW or INS2, you will end up with different amount of gamma.
So there was a square deal rule. So you can get a factor of 100 difference.
Yes. There are other profiles also, like Bino profile, Murray profile. They have many different motivations. You may look at literature and see the blue one is a PISO profile and the green one is Murray profile. So there is almost 4 or 2 order deviation. So if you calculate the gamma ray flux using all of this profile, you have like results which differ by 2 order. That is huge. So this is all because the uncertainties involved in the observation in our statistical data. that lead us to use different kind of or propose different kind of profiles. So there is a large discrepancy between different profile of dark matter density near the center of galaxy. So yes, that is a very interesting point. See, when you are far from the galactic center, all of them converges almost, but the discrepancy appears mostly in the center.
But this is maybe observationally driven, but not necessarily consistent with n-body physics.
But
All of them claim to be those.
for the value of alpha in INS2, they are guided by n-body.
No, that one, the next one.
Yes,
This one is like 4 orders of it. What is it like?
for two orders.
2 orders, huh?
Yeah, 2 orders in the core.
Is this also consistent with n-body?
No, these are I mean led by this observational discrepancy.
Yeah.
Yes,
There may be more leeway.
like structure to some explains better the structures. Of the, yes,
Not in galaxy.
galaxy structure formation.
Inside the galaxy, but structure formation.
No,
is
it's not structural.
Yes, some of the models are also inspired from structure.
But we are trying to do this for the.
This is within a galaxy.
Yeah.
This is within a galaxy. So one such example is forecast problem, as I said. So all this profile, see, this profile is almost flat near the origin. That means like code behavior. But rest of all these profiles are having, are showing the Caspi behavior. Here all profiles are marked, right? So here you have a low zero, constant profile density. So using those constant profile density, you are starting to divert. So this is kind of reference value. Alright?
So how is that pink one? Okay, that's modifying a large.
Yes.
That is also okay.
That is also okay.
How can that be, right? I mean,
Yeah, this kind of
that dotted pink.
yes,
That's
I got it. Yes, this one.
That you're modifying.
This one
large.
shows a large deviation even in the even outside of the galactic origin or galactic.
Yeah, how can that be okay? Because we have reasonably.
Yeah, I need to look at what is all about our 250 profile.
Is that dark matter is ending before our galaxy?
Yes.
Yeah, so that will conflict with all kinds of.
No, it's all our rotation cars.
That I need to do. Well, so the challenges are poor understanding of the background depending on your target, systematic errors, DM distributions in galaxy is not well known. So you can make certain optimizations like enhanced scenario. We can use Summerfield enhancement or bright window enhancement. Summerfield enhancement is a non-perturbative effect when your dark matter velocity is very small and you have a strong coupling among the dark matter and these standard model particles. So your annihilation could be magnified by few orders.
Is there a mass rate for the
I think for larger mass it will be different.
It's also the emitter, right? I mean,
Yeah, mediator. Yeah, depends on the mediator. So for MEV scale mediator, we will have a more amplification.
It's more like you have to take the ratio of something. So
Right.
it's not the absolute mass, but some combination of Q squared, the dark matter mass, and the mediator. So these have to be compared, not that.
As far as I remember that for lower
Yeah, as you said, the velocity, it is a 1 over V kind of.
Right.
Right?
So
So
for
whenever
smaller
you have
velocity,
like
the
1
effect will be
over
larger.
V effect which dominates,
Yes.
you can have.
Yes. And also the coupling coefficient is very important. So when you have a smaller coupling coefficient, you will not see any deviation. Yes. And also for line spectral feature can be observed if dark matter directly annihilates to photon. And thirdly, the regions of space that might contain a large density of dark matter, that is galactic center, or in the vicinity of supermassive object. For example, a supermassive black hole. Supermassive black hole is kind of black hole that has mass 6 to 4 to 8 order of solar mass.
How do you Because supermassive black hole can exist only at the center of a galaxy, right? So why it's so you are saying that so density of dark matter or the supermassive black hole, which is affecting or the joint effect?
The joint effect. The existence of supermassive black hole will invite large density spike around it. That could be useful to amplify your goals. So mainly there are two targets which can where you can look for signatures of dark matter. One is dwarf spheroidal galaxies and other is galactic center. Here your background is less, but the dark matter density is a little low than the galactic center, which has a value 0.01 to 0.1 GeV by semi-cube. Galactic center have a large density, but very complex structure, like very complex background. Typical value of rho zero is little higher there.
The rho zero is what? The central density.
Center.
So they all go to a constant at the center. Is that R equal to 0?
No.
So it's a parameter.
Correct.
Okay. Defined at some radius.
Some radius where gravitational pull is, gravitational influence is. So you can define rho zero.
Yeah, they both, at least the NFW and IMSO both have a place where there is
One.
zero,
Yes.
right?
Yes.
No, in the expression there is a
Yeah. That is,
rho
that
zero.
was there.
Okay. So that R0 and
So-
RS.
For NFW,
What is RS?
RS is the scale radius,
So that is like
below which your profile is cusp.
yeah.
I'm done up to this. So there is a confusion. So is Sagittarius is a SMBH? Here we have a Milky Way galaxy, and at the center of Milky Way galaxies, you have Sagittarius black hole. And it has been, this picture has been taken from NASA website.
So that you confirm with the black hole,
Yes,
not the star.
I confirmed after your call.
Black hole, not the star. Okay.
I was, I mean,
No, he was saying that it is the black hole.
no, I was saying it is a
But I
black hole,
thought it was a star around the black.
but
Sagittarius is Sagittarius, but this is called
Sagittarius
Sagittarius.
A star.
A star is the black dot, which is
Not the star.
close to Sagittarius. In the oscillation of Sagittarius, that's why it's called Sagittarius.
No, independent.
This is the black hole at the center of the Milky Way.
Yes, but there is a star orbiting it. It's 17
Yeah.
hours.
so after your comments, I
What is that star?
There are many stars, right? Is zero, it's
It's the most beautiful.
M87 is also SMBH.
there is that
I have seen that anime.
cloud,
Yes.
it's the oscillation of
Pretty,
Sagittarius.
It's the most beautiful.
Yeah, that's right. It's kind of crazy.
Not galaxy, but not a galaxy.
I will close.
Yes. So in literature, you will find upper limits on your dark matter annihilation strain from the indirect search observation. So you know the flux, and you have seen the amount of flux is function of your dark matter annihilation strain. So using the upper bound on the observed flux, you can put upper bound on your annihilation strain. So here I have this bounds are taken from Fermi paper when dark matter annihilates to BB bar and tau plus tau minus. So you see this is the constraints like 4-year limit, 6-year limit, and the dash line is the amount of cross section that gives you the correct relic abundance. So if you propose a model, you need to check the sigma v. It should be below the allowed limit. So if it goes above this blue line or the black line, which one you believe is the correct one, then your model is rolled.
Wait, what is the blue and what is the black?
Blue is for 4-year data and black is the 6-year data and 1 sigma 2 sigma bounce.
So for these things, it depends on the profile that you have.
Exactly. Okay.
And also the
Yes.
background modeling.
So for accurate analysis, you shouldn't trust this data because the factor you need to calculate the factor D and D, which gives you the differential gamma ray spectrum. that also depends on your model details. But here the bound on sigma b is extracted considering the dark matter either annihilates to BB bar 100% and or tau plus tau minus 100%.
It also means that is from the diffuse.
Diffuse. Yes, true. These bounds have been drawn from the diffuse. Yes.
You will also look at the line.
No.
Well, you should, because that can be very tight, correct? If your dark matter can go to direct.
Yeah.
Then that
But
one
then
can
dark matter mass has to be very light.
Okay.
No, dark matter mass has to be very light. Suppose you want to explain the 511 kV line,
Okay.
then your dark matter has to be order of 1
Is that your goal to explain?
No. My goal is
Yeah,
I'll
if
come.
that's not your goal, then you don't care just whether it's a line or not. Right?
yes, yes,
If it is a line, the bound from Fermi-Lat can be very tight.
yes.
One has to also look at that. In addition to whichever is the tighter bound, right?
But that will happen at MAB scale dark matter. So
Right. I mean, if I have 100 GeV dark matter, I'm relating to
That will also give you.
yes, right.
it will still
But
give you a
to
line
feed
which will
data
stick
is-
out and
But to feed that data is little difficult.
fit. No,
Fit the line
whether
straight
you
up.
have a signal or not, line signal is
Yes.
very sharp.
So suppose line signal is at 511 kV and it is very sharp.
Why? What? It can be anywhere depending on the dark matter. Let's say I take 10 GeV dark matter, 10 GeV annihilation to photon, line will be at 10 GeV, which is a very
Yeah.
sharp spike.
But I'm talking about observation. But
Observation.
in principle, what you are saying, I get it now. In
Right.
principle, when you are summing your like resultant photon spectra, you need to include all the contributions, like light signal and response.
All I'm saying is, for me, gives you a bound when there is a line.
Yeah.
Which is much tighter than from the diffuse.
True.
Because it will stick out, a line will stick
And
out of
that
the
is
background
rule
and
out.
it
You
will
are
be a
saying.
very, very tight limit.
And that would be ruled.
That can rule out your model.
Yes.
So it's not sufficient to only look at diffuse, you must also look at line.
Exactly.
Whichever is the tighter bound, there's a bound on it.
I agree.
That's-
Yeah.
yeah.
Absolutely. Well, I have said earlier that there are three options to boost your dark matter annihilation strength or the resultant photon spectra. One is Sommerfeld or Breit-Wegner. Second is if you have any line signal. Third one is region that contain large density of dark matter, ASMGs. My aim is to consider neutralino dark matter in a MSSM scenario and study its indirect direction prospect around a SMD. I briefly introduced what is neutralino dark matter. MSSM stands for minimal supersymmetric standard model. So we have a standard model in MSSM. You have super partners of all the standard model particles as well as one extra fixed object. The MSSM offers a natural candidate for dark matter universe arthritis concept. Theoretical. The neutral supersymmetric partners of Higgs and electric boson in combination give rise to co-neutralities. So you need to look for stable particles in MSSM. It stands out that neutralino, being the lightest supersymmetric particle, could be the dark matter, and these neutralinos are composition of superpartners of Higgs and electric gauge boson. The mass matrix looks like this. So this is the basis Bino, Yno, and you have two Higgs inos. So mass matrix looks like this: M1, M2, and you have mu parameter in the MSSM Lagrangian mu, Hu, St, and you also have tan beta, which is the ratio of two heads. The composition of the nitrous neutralino eigenstate, as I have already said, that your dark matter is combination of Bino, Yno, Higgs ino, two Higgs inos. Compositions of each will be determined by the value of N11, N12, N13, and N1. Suppose this N13 is very large, then your dark matter will be Higgs ino. I am solely interested on Bino dominated dark matter. For me, N11 has to be around 1. So in this work, we focus on Bino dominated neutralino dark matter in MSSM in the parameter region that can accommodate G minus 2 mu data. Well, G minus 2 mu data, you forget, you ignore the present results and believe the earlier Fermi results, and study the prospect or possible indirect searches through gamma ray observations. See, as mu, as epsilon is nothing but m2 by m1 minus 1. So when your m2 increases or m2 decreases, this epsilon tends to 0 and n12 gets enhanced. So when epsilon is 0, your Bino component in the Bino dominated dark matter will be large. When mu is also close to m1, then your Higgsino component will be large as well. So here are some facts about Bino dark matter. Bino dark matter can give you correct relic density with the lepton coagulations only, mediated by leptons. Also, in resonance region, it could give you the correct relic abundance. So from these 2 points, the M1 and MA, mass of the pseudoscalar, and also lepton masses, they are very important parameters or crucial parameters for this study. Now, if you switch on the M2 or if you reduce the M2 towards your M1 value, then Bino Wino mixing will be relevant as well. That will induce Bino Chargino coagulation. Little admixture of Higgsino controlled by mu. So if you bring the mu value closer to your M1 value, that will help in boosting the direct search cost. Importantly, gamma ray flux from dark matter pair annihilation completely depends on how much Wino or Higgsino component you have. Combining all, we have these crucial parameters M1, M2, mu, tan beta, ml tilde. Ml tilde is the mass of the lepton. So you have 5 crucial parameters. Other parameters in the MSSM, you can consider it maybe around TB or more than TB scale.
So if you have a pure beam, you cannot get an indirect signal. Is that what you're saying?
Yes.
Last point.
Yes.
Why is that? I can have a 3-body photon emission still, right? 2 Binos annihilate to, let's say, leptons. Is that possible?
Leptons, then 2 Binos, but the vertex will be proportional to how much Higgsino you have.
So if it is a pure Bino, I cannot get 2 leptons.
No.
Why?
That vertex, as I said, Bino, Bino, then it will be mediated by Z, right? And Z to electron, the vertex will be proportional to N13 square mod of N13 square minus mod of N.
So, great. So 2 Bino can go to Z. There is a Bino Z vertex.
Yes,
Then Z can go to L plus L.
yes, Z can go to L plus L minus.
L can emit a photon.
Yes, we have, I mean, this was an obvious question. So we have checked somehow that this process has vertices involved, which is proportional to your mod N13 square minus mod N14 square. So when you switch up your Higgsino from appearing, then it comes out to be zero. Yeah, so that all depends on your vertices. So we have to open a list, I mean, book.
No, if there is a Bino Z vertex, then there is
So Bino
which is input.
No, Bino Z vertex. You need to check the Bino Z vertex.
Whether it's there or
yes, whether it is there
if
or
it is there, then there is no
it is proportional to which factors in the picture. Yeah. So G minus 2. So MSSM can in
there is no
principle.
BBZ vertex.
Yes. So that is the catch.
There is no BBB.
That could be the catch.
U1 cannot have a BC.
So in MSSM, you can accommodate the G minus 2 muon anomalous magnetic moment. So until the recent results from lattice collaboration, we have enough motivation to consider G minus 2 mu as an indication to cultivate beyond standard modeling. So here you see at one look, your neutralino as well as leptons appear, which give you to fill up the contribution of delta mu. Delta mu is the excess beyond the standard prediction. So in MSSM, at one loop, delta mu turns out to be this, which is proportional to tan beta as well as lepton mass square and this is mu1 mass square divided by m SUSY square, where we have considered all the SUSY particles having a common mass scale. So it tells you when tan beta is larger, you may have enhancement to the value of delta mu, as well as when your SUSY scale is smaller, then you can also have an enhancement.
So by the way, you can always go towards delta mu 0 and if
Yes.
the current lattice thing folds up and then you
Yes,
don't
yes.
have a discrepancy.
Yes, then your model is
Always
still
go to the-
your model is still valid, but here we want to accommodate this delta mu value of the SUSY.
Okay.
But it can't be greater than what the experimental sees.
But can we extend it like difference? Don't need to go to the standard.
Yeah, but it has left that can give you a dark matter. In the model you are talking about, that can't give you a dark matter.
That is fine. But the neon G minus 2 is not only the motivation, there is other motivation.
Yes, this is not a motivation, but to restrict your parameter space more, you can consider the other BSM observation.
I would say this one should not be used to restrict your parameter space. Because now we know from the lattice result that there is no discrepancy with the standard.
I know absolutely.
This slide-
That's why I say that.
But this slide also should not be shown.
No, but still the calculations are.
This has to be constantly parameter. Because it has a conversion to C minus 2, which is no longer there. So it should again be used constant.
Yeah,
But still.
but he's not using that.
No.
Yeah, he is trying to motivate
He
you.
doesn't work at the speed of light, right? Presumably he calculated this when there was a
Yes, that is so. And another thing is,
No, but now since it knows that there is no point. in
no,
doing
no,
this,
another thing is,
Another slide is motivation.
No, it's possible that lattice has got it wrong and then we'll go back to distribution.
yes. So there are
No, but there has been huge amount of discussion
That's right.
last 3-4 years.
I agree.
We can only hope, right?
And so still the things can, I have seen things which have been found to be wrong after 15 years. So even after 1 month, you can still.
And that is,
Anyways, please proceed.
I am trying to
we
keep.
are very,
Let him finish his.
I am trying to keep the doors open. So even if lattice calculation turns out to be correct, but then also you may have a significant contribution to your delta mu value, right? Or mu value. That has to be kept below the experimental limit, right? So there is always some motivation to look for G minus 2. Otherwise, a particular parameter space can give you a larger mu which is not. So data is still relevant to restrict your.
you have constrained your
No,
parameter space by that.
no, because that came out very recent.
It's not recent, it's already 6 months.
No, I don't think it is 6 months.
Yeah.
Okay, proceed.
The Budapest hypothesis.
Okay, all right. We may have.
No, we should not show all this data when the updated value is there. It shows no, this is.
No, it's not when there is a lattice person involved.
No, I don't think
Otherwise,
so.
But
It's not even lattice or anything, it's like.
It may be right. No,
Yeah,
limits, right? This was the historical motivation, so what he says is right. That whatever delta, now he says delta mu is 0, his parameters must still be within that limit.
Yeah, that's what
That's
is
the correct
updated.
statement.
no, Sayantan, he agrees with you.
yes, I agree with you.
Yes,
As I said before, that if you ignore the descent result, then you can this calculation is still.
Which is why I was asking whether if you can accommodate delta mu to the 0. He
Yes.
says he can still accommodate.
Yes,
Regional
but
parameters will change,
yeah.
but the things won't go. It will just slightly shift.
I'm
Parameters
fine with
will-
that.
Yeah.
So
Which
that's
I
why
know
I'm
that
saying
you
the
can
data is still
predict.
relevant. If lattice science calculation turns out to be correct, I may have some parameter space what I have obtained that will go well. So, but my motivation is not to explain the G minus because it is very well known that
That is why I-
MSSM can accommodate. Now I'm coming to my motivation and it will take another 10 minutes to complete. Well, so motivation of the work is in your conventional Bino dominated dark matter, you always end up with 10 dark matter photons, 10 photon signal in the inside DSP of the galactic. So the we are particularly interested in exploring the detection prospect of neutrino dark matter around the Milky Way supermassive black hole in galactic center. Our aim is to find out the requisite amount of spike for Fermi or Higgs. So if you Bino dominated neutrino dark matter, if you want to exclude from either Higgs or Fermi data, then how much spike is required? That will.
So is
Yes.
that because our galaxy is the most relevant, or like what if a dwarf spheroidal can give you a better signal? Have you checked that? Or?
No, I have not checked that. A different galaxy can give a better results as well. But I have checked with this DH speech and galactic center, and that give you very fancy.
And our galactic center signal is the best
Yes.
in okay.
I think it's 1/x squared, right? The flux will be very small if you put so your own
But
galaxy will
as
always be
Manjari
the
keeps
best
pointing
galaxy.
out, our galactic center for us is a very busy place from background. So if you look at some other galaxies, sometimes you can get a better.
In other galaxy, 1/r squared, your flux is decreasing by some factors of orders of.
But backgrounds are the better.
1/r squared is
Yeah,
everything.
it's not wrong.
Oh, but whatever objects appear in our galactic center, those will be at the center of other galaxies, right?
No, you're not looking at part of it. You're looking at the full galaxy.
Sometimes
You're not going to look through in the line of sight a lot of
Actually,
time.
the dwarf galaxies are very clean system.
Yeah.
Yes, I wanted to talk about that. Sometimes dwarf galaxies give you better results.
They are very clean.
Yeah, they are very.
They are not crazy. Because they are.
Yes. So this is the very crucial slide.
So how many?
Oh, how many draws? I use that Draken draw. So here is the density profile of what I have used. The blue one is the generic NAW profile. So if we define it inside the capture region, there is no dark matter, and outside some particular radius RB, it follows the NFW, and inside, with the variation of gamma SP, you see a spike. So once you increase gamma SP, the spike is good. There is an
There is mean type of thing you are calling that spike.
no. See, this is the NFW up to RB. Our profile matches with NFW. So then you switch on the gamma SP, you find an enhancement.
Yes.
Which is almost 4 order larger than the.
What is gamma SP?
Gamma SP is the spike parameter here. So rho SP is the rho RB. Rho RB means the density here and spike.
Is there any motivation for this?
Yeah. So this is the generic spike profile.
What is the motivation for it?
Motivation for it means because SMBH has a larger gravitational pull.
So what is because SMB
SMB supermassive black
okay.
has a larger gravitational pull. So you expect that density spike to exist. Yeah.
What about what thing?
Yeah. So the range. Yeah. The range is fixed by this value of gamma SP parameter. So it has a range like 1.2 to something 2.5. Yeah, sure.
So rho B is the density at RB, right?
Right.
And what is rho B?
Yeah, I'm saying that. Now, if you simply follow this power law, you will have a uncontrolled like behavior. So around the center, the spike will be like the here. But that cannot happen because when the spike is more, when there is more dark matter number density, the dark matter annihilation rate is also large. So there will be competition between the dark matter annihilation rate and the dark matter number density, and that will make the dark matter density near the origin to flatten.
Right. So how did you get that RB or whatever?
Yes, this RB
is a complete input parameter or like
that is an input parameter from n bodies. We have
from n bodies.
We have used
that they tell you that maybe there can be a departure from NFW at that RB.
Exactly.
And in order to match some other data.
Some other data. So we have used that particular value.
I see.
Well, So since the spike is confined to a very small region, so you can expect the flux to appear mostly from this region.
Yeah, something like 6 centimeter.
That's why the spike is confined to a very small region. Compared to the galactic scale, this is still very small.
So Manjari's question, why didn't you plot it in micrometers?
So what happens from 0 to 10 power 12?
No, that is a
It's all
capture
zero,
region.
is it?
Capture region.
Capture. Okay, that whole region is captured.
Well, since the flux is mostly confined around its origin, you expect that flux originates dominantly from this region. So we can consider it as a point source compared to the usual angular resolution of Fermi-Land. So under the assumption of single point source, this formula can be used to calculate your gamma ray flux. Now see, this particular profile includes rho in, and rho in depends on at which rate the dark matter annihilates. So here in your J factor, particle physics inputs enter. That makes it different from the usual dark matter density profile.
Sorry, but the line of sight to the center of the galaxy is like a lot of gas and dust, this and that. Will that gamma ray make it to Fermi-Land? I mean, that is to be
So Fermi-Land has a dedicated point source
towards the center of the
towards the
galaxy.
center.
Say background.
Yes.
They do the modeling from the
Yes,
background.
yes. So that is different from the usual diffuse space
And they give you the
bounds. How much flux we can. So they also, I think, considering this kind of profile, they give us a bound. Yes. So this plot is to depict that J factor indeed depends on the particle physics inputs like dark matter annihilation, interaction strength, and dark matter mass. So you know MSSM has a huge parameter space. We consider two kind of scenario when I know is missing in the first case and I know is present. So we picked up 6 benchmark points. So this benchmark points shows you that all the dark matter masses are in sub GeV BGI, and also it gives you the spin independent direct cross section within the allowed limit and gives you correct relic as well.
So this is on G, right?
This is all GeV, yes. So when we compute, it is around the required order. This column.
So this is the relic density is arranged by co-annihilation.
Yes, and then for Bino dark matter, purely Bino kind of dark matter, co-annihilation matters with flaps.
Tau.
Tau. Mu1 input is mu1. For Bino, I know there will be additional co-annihilation.
So if you mix muon, then isn't there a problem with G minus 2 and all that?
That we have to take care of. We have taken care of. This is possible, still possible. We have taken care of. Yeah. So with these 6 benchmark points, when you calculate the sigma v and use the available upper bounds for conventional profiles, we see that the calculated cross sections lie like orders below than the available bound. So this indicates that in a conventional dark matter profile, this will produce a very faint signal which will never be detected.
How many orders of magnitude lower?
Minus 28, and bound is around the lowest bound is around 20 minus 50. So 2 orders.
2 orders.
Yes. Yeah.
So you cannot boost the dark matter by 2 more orders of magnitude? You can, right?
Yeah. By other mechanisms.
No, I mean you just artificially jack up your curve, your power law curve that you have.
Yes.
You can jack it up.
Yeah. Yeah.
What
Gamma
is the
SP ultimately is giving that one.
Yeah, there is no constraint, right?
No, but when you are talking about SMP, there is a constant. How much spike you can have?
Yeah, what is the constraint?
Gamma SP value, as I said, it has to be lower than 2.5.
Sorry, what has to be lower than 2.5? The power.
The power.
And that's from where?
That's for n bodies.
Oh, from n body.
So this red line is Fermi bound, and this green line is Hess bound. So in each energy beam, we have calculated the gamma ray flux for 6 benchmark points. considering different gamma sp values, you see when gamma sp is 2.1, only one benchmark point is ruled out, like BP1. BP1 is ruled out. But once you start increasing the gamma sp, other benchmark points also get. So it tells you that indeed a spike can give you either Hess or Fermi exclusion. I'm skipping this. Finally, we did a scan for the Bino-Hixinox case and find out only these points which satisfy everything, like all bounds, experimental and theoretical. The thing here is important that for
It's on the y-axis.
Lepton mass. So you see a linear behavior between the lepton mass and your neutral mass, because as I said, the lepton coannulation matters for Bino dark matter in order to satisfy the Rayleigh. So almost it gives you a linear plot. In the right side, the plane is same, but here the colors indicate the required gamma sp value. So to rule out this data, you need gamma value around 2.4, gamma sp value 2.4. So gamma sp around 2.4 rules out this parameter, and for this, the highest possible neutralino mass for Hess or Fermi exclusion, you require gamma sp around 2.2.
So lighter the mass, the gamma ray energies are lower. Is that why you need a larger gamma sp?
No. It also depends on your Fermi and Hess data, right? Fermi data can't go beyond 100 GB.
Okay.
See,
100.
100 GB. It is 100 GB. So Hess starts from something 180 GB. So there is a gap. So you can't really tell you that regular is the behavior is regular. So you can find here little irregularity, because see.
No, I'm asking probably a simpler question. So I'm just asking, why do you need larger gamma sp as you go to lighter mass?
All right.
Yeah, what is that?
Yeah, larger gamma. So you are saying larger gamma sp requires lighter. Oh, okay.
Yeah.
So you say larger gamma sp means it is more likely to be out by the Fermi data.
Okay.
It is more likely to rule out by Fermi data. So
because
so Hess measures the.
Okay.
So Fermi data. Yes. So
Fermi is sensitive to lower energy.
lower.
Yeah. Okay.
So that's why the behavior is different.
So as you lower the mass, the gamma ray energy is lower,
Yes.
and so you need a larger gamma in order to be ruled out by
Fermi or Hess. In this case, mostly for lower dark matter, it will be Fermi. And for Bino-Hixino case, the linear relationship is not there, because you have more freedom, because there will be more coannulation channels, like with charginos, heavier neutralinos, as well as with leptons. So there are many scattered points here. And also in this plot shows you the requisite gamma sp values to know each of the points.
So this correlation is only due to Rayleigh density, right?
Yes.
So
here,
how is this relevant for gamma ray spectrum?
Yeah, this M2, all parameters enter in your gamma ray spectrum. The calculation of your because here, I mean, you have the scope of Chargino coannulation as well as lepton coannulation. So you don't have any linear relationship. So here also you require the requisite value of gamma sp is more than 2.1. Finally, I'm concluding. So in Bino-Hixino, a precise adjustment of the lepton mass is essential to facilitate effective lepton coannulation. In Bino-Hixino case, one has more freedom due to the presence of light charges. In conventional galactic halo, Bino-dominated neutralino dark matter produces faint signal. The situation can be improved drastically in presence of a dark matter density spike around an SM beach. In the Bino-Hixino case, after accommodating all the constants, the allowed mass range is 120 to 360. For Bino-Hixino, it is a bit enlarged, which is 120 to 530 GB. The required value of gamma sp is around more than 2.1. It has to be 2.1. Thank you.
only for our collection.
Which one?
This particular data, whatever is only for our, not for overall.
So what is the direct detection prospect for these things?
Yeah.
You have a Bino dominated dark matter.
Yes.
Is
So
direct
when,
detection
when you have a pure Bino dark matter, your detection cross-section will be very subtle.
for the things that you are using?
Yeah, so there could be complementary scopes,
Yes.
right? So if you find it in detection,
No, but I'm asking for the parameters that you have chosen. What is it? Like, is it still allowed? Is it like suspect?
it is still allowed. In the table, I have listed the direct detection.
How close is it to the limit?
Yeah, it is like 2 order smaller than the
2 order.
but still above the
Hmm?
still above
Still above?
the neutrino flow.
Okay. Is the next round going to?
And general in some mass scale, I heard the generality already touched the
Generality has
neutrino flow.
already gone, that's the blueprint.
Oh, which means that it may have excluded these points.
For a particular mass only.
Okay.
For a particular mass, generality has touched the neutrino flow. That's the problem.
It's that side.